Hello friends and welcome to CEC live lectures. In the ongoing lecture series on extraction of natural products, till date we have discussed about the basic principles and some fundamentals about extraction process. That is, whenever a drug powder is dipped in a solvent, what are the processes that take place. We also discuss about the ideal characters of a good extraction technique or a process, and also the characters of the menstruum or the solvent that is used to extract the drug powder. We also discuss about certain conventional extraction techniques, that is maceration, digestion, decoction, infusion, percolation, soxalate extraction and reflux. And in that we discuss about their principle, what are the factors that affect their extraction efficiency, how the extraction efficiency can be improved, what are their advantages and disadvantages, and followed by some of the modifications of these conventional techniques with respect to their industrial utilization vis-a-vis the hyphenations with some of the modern techniques. After that we started with the modern extraction technique, wherein I started with ultrasound assisted extraction, and we discussed about the brief historical development of the utilization of ultrasound for extraction purposes, what is the principle behind the ultrasound assisted extraction process, that is how ultrasound increases the efficiency of an extraction process, what is the instrumentation that is involved in setting up an ultrasound assisted extraction instrument, followed by factors that affect the ultrasound assisted extraction, and in the last we discussed the applications of ultrasound assisted extraction technique in various facets of applied sciences. So friends, in continuation with the lecture series and on the same lines, today I'll start with another modern extraction technique, that is microwave assisted extraction. So in this lecture we are going to discuss what are microwaves, and I'll give you a brief historical development of microwave application with respect to their use in extraction processes. This will be followed by the principle of microwave extraction, that how microwave extraction improves the extraction efficiency over the conventional techniques. Then I'll discuss about the instrumentation, what are the components that are involved in making up a microwave assisted extractor, what are the factors that affect the microwave assisted extraction. Then we will discuss certain modification, and in the end we will discuss about the applications of microwave assisted extractions. So coming on to what are microwaves. Now microwaves are nothing but these are electromagnetic radiations which are non-ionizing, and they have a broad frequency range ranging from 300 megahertz to 30 gigahertz. And if we further talk about their peculiarities, then microwaves, they have, as I told you, that these are electromagnetic radiations, they have electric field which is perpendicular to a magnetic field. So this is one of the major characters of microwaves. Now this frequency 300 megahertz to 30 gigahertz, this is largely used in telecommunications or radar transmissions. And we know that apart from these important uses, microwaves are commonly used in household for heating purposes or for cooking food. And since they have a very broad range of frequency, specific range of frequency was set up for the non-telecommunication uses. And in Europe this is 915 megahertz to 896 megahertz in Europe. And by and large, most of the industrial, scientific or medicinal applications of microwaves are restricted to a frequency of 2.4 gigahertz. Or in simple words, if I say that majority of the microwave ovens or the microwave extractor or the microwave synthesizers that are being used in laboratory or in industry or in medicinal areas, they have a frequency of microwaves that is 2.5 gigahertz. And this categorization of frequency is largely done so that whatever telecommunication use of microwave is there, the frequency that is used for such purposes should not interfere with radar telecommunications or other telecommunication services. Now since the frequency that has been set, or I will say ISM frequency, that is industrial, scientific and medicinal frequency, that has been set aside by the agencies, that is 2.45 gigahertz. Now this frequency of microwave, they have a very low amount of energy, and when we say that they have a very low amount of energy, it means they are not able to break the weakest bonds that are present between the compounds, which we can say that they are not even able to break hydrogen bonds. And the energy that is present with these microwaves of frequency 2.45 gigahertz, that is just sufficient to cause the rotation of the molecules, and not even the vibration, but only the rotation of the molecules. And how this rotation helps in heating up the contents, that we will discuss further. Briefly, I'll tell you that these rotation of the molecules, they just causes an increase in the friction, which leads to the heating of the mixture. And therefore we can say that microwaves, since they have a very low energy which is only responsible for the rotation of the molecules, we can say microwave irradiation or the use of microwave is strictly related to the conversion of electromagnetic energy to the heat energy. And how this occur, that is the conversion of electromagnetic energy to heat energy, we will discuss further. Before we move on to the mechanism of microwave assisted extraction, I'll just give you a brief overview about the historical development of the use of microwaves. Now, it all began in 1886 when Heinrich Hertz, who is a German physicist, he discovered that radio waves could be reflected from the solid objects, and this laid the foundation of development of the radar technology. Then a Russian physicist also developed instrument which he was developing for communication between two ships, and he observed that there is certain disturbance in the signal which is largely due to the obstruction that was present between the two ships. Though he did not work upon this observation ahead, but again this also laid the foundation for the discovery of the radar technology. Then Butement and Pollard in 1930, they developed a prototype instrument which emit these radio frequency or microwaves at a frequency of 600 megahertz. Though this was only at the laboratory scale, but again this was a major development. Another major development took place in 1937 to 1940 when a British scientist, Sir John Turton Randall, he developed a multi-cavity magnetron, and magnetron is nothing but it is considered as the heart of microwave, the equipment that is responsible or the part of the microwave which is responsible for the development of microwaves. Now he developed a magnetron, though this magnetron was largely used for the communication through a radar during the World War II, but this was the first instant when specific magnetron was developed. And by this time the use of microwave was further enhanced in the radar development, because as I told you that earlier the radar telecommunications were mainly through the radio waves, but since microwave were found to be more efficient in penetrating the objects, therefore the use of radio waves was shifted towards the microwave for the radar telecommunications and radar development. It was in 1940s when an American scientist, Percy Spencer, who accidentally discovered that microwave also cause heating effects. What happened was, he was working in his laboratory for using a magnetron for further improving the radar telecommunication. He was initially working on radar telecommunication only. So he was having a peanut bar in his pocket, and while working on that magnetron to improve the radar frequencies, to improve the radar telecommunications, he accidentally found that the peanut bar which he was having in his pocket was completely melted. So he was quite intrigued with this observation, and he believed that it is something to do with this magnetron or microwaves that are generated by magnetron. So next time he again took eggs in his pocket and he started working on magnetron. And to his surprise, he found that after some time the eggs explode. So now he was more sure that these are nothing but the heating effect of microwaves that led to the explosion. He again repeated the experiment with certain cones, and those cones were completely popped out whenever they were exposed towards the magnetron or the microwaves that are generated by the magnetron. So he found that microwaves have a specific heating effect on the objects, and this led to the development of the microwave ovens, and the first microwave oven which was named as radar range, because this discovery or this development took place by using the magnetron that was meant for improving the radar telecommunication. So this was the instant how the microwave ovens come into the picture. And during 1950s there was enormous increase in the utilization and the commercial use of microwaves for heating and cooking. But it was in 1975 when Abu Samra and his group, they utilized microwave beyond its cooking abilities. So they used microwave radiations for preparing ash of biological samples which they want for the elemental analysis. So this was the first instance when the non-cooking or the non-domestic utilization of microwave was there, apart from the telecommunications or the radar communications. Perhaps it was Gansler in 1986 who first reported the use of microwaves for extraction of natural products, and he extracted crude fat, vicin, convicin and gossypol from the seeds and food and feeds using an organic solvent. And he found that the 3.5 to 4 minute irradiation with microwave was better in extracting out these components in comparison to extraction that was carried out using soxolate for more than 3.5 hours. So this was the first, perhaps this was the first report of utilization of microwave assisted extraction. Later in 1991, Pare and his group, they compared the extraction efficiency of microwave assisted extraction vis-a-vis to steam distillation when they extracted out essential oil from Mentha piperata. And they found that the yield was 94% in case of microwave assisted extraction, and not only the yield was tremendously increased, but the quality of the oil that was obtained just after 40-second irradiation with the microwaves in comparison to the steam distillation that was carried out for approximately 2 hours. And later in 1995, Pare and his group patented the use of microwave for the extraction of natural products. So this was how over the period of time, the use of microwave, starting from the telecommunication, radar communications, it entered into the non-telecommunication uses, following through the application in cooking or domestic heating to the extraction or the pharmaceutical industry or the medical industry. Now this graph also evidently shows you that how the use of microwave assisted extraction has tremendously increased over the period of time. If we look into the initial years of discovery, that is 1991 to 95, only there were approximately 1700 articles that were published mentioning the use of microwave assisted extraction. In the next 5 years, this figure was almost double, or rather more than doubled, to approximately 4100. Then in 2001 to 5, again tremendous increase, approximately 8500 articles were published mentioning microwave assisted extraction. Then in next 5 years, the figure was again doubled to 16,000. You can again see that there was continuously doubling of the figure over the period of time, and in 2016 to 20, approximately 56,000 articles were published on Google Scholar that were mentioning the microwave assisted extraction term. And in the last 2 years, we have seen around 25,000 articles that have been published which have used microwave assisted extraction for one purpose or other. So this is how the use of microwave assisted extraction technique has been tremendously increasing over the recent past. Now, as I told you that microwaves have a very less amount of energy, and they largely depend upon the conversion of electromagnetic radiation into the heat. Now this conversion of electromagnetic radiations into heat largely depends upon three major factors, that is permittivity and permeability of the compounds or mixture, strength of electromagnetic field, and geometry of microwave reactor or the instrument which we are using. So permittivity is nothing but the ability of a compound to absorb or to behave in an electrical field, whereas permeability is an ability of the compound to behave under the magnetic field. Whereas the strength of electromagnetic field, obviously it will also directly impact the conversion of radiations into the heat, and last but not the least, the structure or the geometry or the instrument which we are preparing, all those factors, they affect the conversion of electromagnetic radiation into heat. or in simple words we can say these factors will affect the heating efficiency of the microwaves. Now, but the question is how these microwaves cause heating of the subjects or the compounds. Now, this conversion of or the heating by the microwaves is largely due to two phenomena, that is ionic conduction and dipole rotation. So, as the name indicate, ionic conduction means this is the electrophoretic migration of the ions when an electromagnetic field is applied. We know that whenever electric or a magnetic field is applied, the ions they tend to move. So, this kind of migration is known as ionic conduction, and during the course of their movement these ions collide with each other, which cause an increase in the friction, and this increased friction tend to generate heat. This is one mechanism. Second is dipole rotation. So as the name indicate, and as I told you that microwaves have an ability only to cause the rotation of the molecules. So it will cause rotation of only those molecules which have dipole moment, and we know that most of the polar compounds they have a dipole moment, and whenever these dipole moment containing compounds or molecules or the polar molecules are exposed towards microwave radiations, they try to align themselves in the direction of the field, preferably electric field, and this kind of alignment of these ions is known as dipole rotation. Now, since these are nothing, these are waves, so there will be certain phases where there will be a decrease in the strength of the field followed by increase in the strength of the field. So whenever this field or the strength of the field decreases, the thermal disorder is restored. It means the ions which aligned themselves in the direction of electric field at a particular strength, and when that electric strength of that electric field decreases, again those ions they turn back to the random order or the disorder, and this we call it as thermal disorder. And this thermal disorder is restored whenever the electric field is decreased, thereby causing release of the thermal energy, and this release of thermal energy also helps in heating up of the contents that are exposed to microwave assisted extraction. Now you can clearly see the figure, the first figure, that is A. This will represent the normal condition of the ions that are in a medium, and whenever they are exposed to a particular field, they align themselves in the direction of the field, and when the field is decreased, you can see in the third picture, again these molecules are disoriented or the thermal disorder is restored. And it has been found that at the frequency of 2.4 gigahertz, this thermal disorder or the alignment of the ions and followed by their thermal disorder, this phenomena occur in a cyclic manner, and it occurs at a tremendous high pace of 4.9 into 10 raised to the power 9 times per second. So this tremendous speed of alignment and disalignment causes to rapid heat whenever the subject or the components or the solvent is exposed to microwave irradiation. So this is how microwaves cause heating in the whatever components are being exposed towards the microwaves. Now I have told you that there is a release of thermal energy. It means the heat is released, or whenever the ions collide with each other, they generate heat, and whenever the electric field strength is decreased, thermal disorder is again restored, and they release thermal energy or the heat energy. Now this release of heat energy is defined as loss of heat, and this loss of heat has been quantified by a factor which we call it as dissipation factor, and this factor was given by Kingston and JC. Now this dissipation factor is designated by tan delta, and it is the ratio of epsilon double prime to epsilon single prime, wherein epsilon single prime is nothing but the dielectric constant of the solvent, and epsilon double prime is the dielectric loss factor, which expresses the efficiency of transformation of electromagnetic energy into heat energy. So whatever heat is dissipated, whatever heat is lost on restoration of thermal disorder, that is designated by the epsilon double prime, which is also known as dielectric loss. So we can say that if a substance is having a high dielectric loss, it will have high dissipating factor. Higher dissipating factor, it will lead to more heating or overall heating of the mixture. Whereas if a compound is having high dielectric constant but a low dissipation or the dielectric loss, then the overall dissipation factor will be less. Now this relation can be further explained by taking example of certain solvents. Now you can see that higher dielectric loss, higher will be the dissipation factor and more will be the heating. So the polar solvents like methanol, DMSO, ethanol, they have a high dielectric constant in comparison to non-polar solvents such as hexane. Therefore, these polar solvents strongly absorb the microwave radiation and easily get heat up. Whereas hexane, which do not have any or practically nil dielectric constant, it will not lead to the alignment or restoration of disorder of the ions. Therefore, such solvents will not heat up, and therefore the non-polar solvents like hexane, they are termed as microwave transparent solvents, and the polar solvents which absorb the microwave, they are used for the extraction purposes. Now we talk about water, which is an interesting solvent in case of microwaves. Now water is a highly polar solvent, therefore it will absorb microwave more in comparison to other polar solvents like methanol or ethanol. But on the contrary, water has a low dielectric loss value. It means water will absorb the microwave radiations, it will get heated up, but it will not be able to dissipate that heat to the mixture. So we can say water can cause the localized heating of the objects, and therefore presence of water is essential for microwave assisted extraction, but pure water will not lead to a better extraction. This I can explain further. So in this table you can see the dielectric constant and dielectric losses of different solvents, starting from hexane towards the most polar, that is water, and we can say on the extreme right, that is the dissipation factor. Now the dissipation factor of methanol, which is having dielectric constant almost half the value of that water, but the dissipation factor of methanol is much higher, approximately 3 to 4 times higher than water, and this is largely because methanol has a higher dielectric loss value in comparison to water. And since I told you that water will cause localized heating, this effect is known as superheating effect. Now I will explain you that how this water will help you in extraction process. Now whenever we use a drug, it contains small amount of moisture. Now, this moisture or water that is present in the drug particles, they will absorb the microwave radiations and they will start heating up, but they have a poor dissipating factor, so they will not dissipate the heat. On the other hand, they will keep on heating the drug particle from inside, and at a particular stage this water will completely get evaporated, leading to the formation of steam. This steam will increase the pressure inside the cell and will cause the rupturing of the cell walls, thereby releasing the cellular content into the solvent. And this is how microwave assisted extractions takes place. Now this conversion of electric energy into thermal energy is further described by Chan and his group with the help of this equation, which is nothing but product of certain terms, where P is the microwave power dissipation per volume unit, K is the constant, F is the frequency of the microwave that is being applied, epsilon 1 as we prime 1 as we discussed, it's a dielectric constant of the material, E is the electric field strength or the magnetic strength, then tan delta is nothing but the dissipation factor or the dielectric loss. So the product of these terms is equivalent to the power dissipation per volume unit. Now apart from this dissipation factor or dielectric loss, another factor that is important for the microwave heating is the depth of the penetration of the microwaves. Now the penetration depth of microwave is defined as the depth into a sample where the microwave power drops to 1/8 of its value present on the surface. Now if we have a setup wherein the microwaves have a very less penetration depth, then obviously the substance that is under microwave irradiation will have only heating effect on its surface rather than into the depth. And this equation clearly shows the relation between the depth of the microwaves to the wavelength in the vacuum of the microwaves. So this is basically how the microwaves and the major factors that can affect the heating, they are interrelated with each other. Now you can see that the depth of penetration varies inversely with the loss factor and is even less when the product is sensitive to microwaves. So lesser the loss factor, more is the depth of penetration. Higher the loss factor, lesser will be the depth of penetration. So if the penetration depth of the microwave is much less than the thickness of the material, then it will only cause the heating of the surface, and rest of the material will be heated by the conduction effect. That is, from the heat will flow from the surface to the inner part of the material, and the inner part of the material will not be heated by microwaves but just by the conduction of the heat. So friends, in the next lecture we will further discuss about various other aspects of microwave heating. Thank you.